welcome to the deep dive.
Thanks for having me. I'm really looking forward to this one.
Yeah, we have an incredibly unique journey prepared for you today. And it's one that requires us to completely abandon the standard operating procedures of software development.
Right, entirely.
Because usually, when people want to understand how a piece of software works, what do? They open up an integrated development environment.
Yeah, an IDE.
Exactly. They look at high-level languages like Python or C++, and they just read the code.
Which is the normal way to do things.
Right. But today,
Yeah.
we are strictly adopting a sort of a don't read code philosophy for this session.
I love that framing. Don't read code.
Yeah. We're stepping entirely away from the comfort of abstraction because we really want to take you down to the bare metal.
It's a necessary shift in perspective, I think, because when you spend your time looking at abstract software syntax.
Which most developers do.
Right, whether that's, dense lines of REST traits or carefully organized object-oriented classes or even inline assembly language, it actually provides this deeply false sense of security.
A false sense of security. Wow.
Yeah, because software syntax is fundamentally just a polite negotiation with the machine.
A polite negotiation.
Exactly. It hides the brutal, unyielding physical reality of what the silicon inside your processor is actually doing at a microscopic level. It obscures the raw physics of, electricity flowing through microscopic logic gates.
That polite negotiation is just such a perfect way to frame it. Because software development, it wraps everything in this diplomatic language.
It really does.
If you make a mistake in a high-level language, the compiler gives you a helpful little error message.
It stops you before you hurt yourself.
Right. It stops you. But our goal today is to understand bare metal SIMD, single instruction, multiple data processing.
Which is a whole different beast.
It really is. And to truly grasp how electricity physically flows and manipulates data at that atomic level, we have to strip away that polite abstraction entirely.
We do.
We have this massive stack of sources in front of us today. We've got architectural breakdowns of modern CPUs.
Hardware optimization manuals from the silicon manufacturers.
Yeah, and these deeply technical design documents. But we're not going to read a single line of that syntax to you.
No syntax today.
None. Instead, to help you understand these incredibly complex microprocessing concepts, we are going to map every single one of them directly to the mechanics of a game world.
This is the best part.
Specifically, surviving an ancient collapsing palace filled with deadly traps, magical elemental powers, and hordes of cursed sand monsters.
It serves as the absolute perfect conceptual lens for this architecture.
It really does.
Think about writing standard, safe code in a high-level language. Conceptually, that is like standing safely outside the massive stone walls of that ancient palace.
You're safe on the outside.
Exactly. You're sitting at a sturdy wooden table, reading a pristine, well-lit map of the interior. And crucially, you have a mentor standing right over your shoulder.
Okay, I like this.
The compiler is that mentor. It's constantly checking your math, stopping you from making a bad jump, and actively preventing you from routing yourself into a lethal trap.
Right, so if you try to walk into a spike pit,
the mentor grabs your shoulder and says, no, that memory is out of bounds.
You are totally protected. But bare metal SIMD programming, that is what happens when you leave the table and step entirely inside the cursed palace.
You're in it now.
You are the one executing the wall runs. You are swinging the curved swords. You are manually manipulating time and elemental magic in real time.
Down to the absolute millisecond.
Yes. And out there in the collapsing corridors, there is no mentor.
None.
The hardware makes no guesses, and it offers no warnings. You are dictating the electrical flow yourself.
Which is terrifying, honestly.
It is. Because if you miscalculate the physical jump, or if you route the wrong voltage to the wrong gate, the entire world shatters around you. The simulation just crashes.
Which means the stakes are absolute. There is no handler to save you when you're writing bare metal routines.
Right.
So before you even open the heavy wooden doors to engage the enemies inside, you have to meticulously prepare your elemental loadout.
Which brings us to the first conceptual phase of our deep dive, something we can call the ancient forging anvils.
The anvils, yes.
When developers first start working with SIMD architecture in the systems language like Rust, the very first thing they encounter is this intimidating wall of syntax.
The trait bounds.
Yes, trait bounds. I want to set the scene for the listener here. If you look at the documentation for these hardware instructions, you see this massive chain sequence of requirements.
It looks awful to read.
It does. It looks something like, copy plus clone plus add plus output equals self.
Yeah.
For developers who are used to standing safely outside the palace, looking at their map, they usually see this as a boring software checklist.
Just administrative chores.
Exactly. Chores they have to satisfy just to make the red error lines in their text editor disappear.
But once you're inside the palace environment, you realize this isn't a checklist at all.
Right.
This is the strict ancient magic of the palace's forging anvils. These are the absolute unbreakable laws of physics that govern your elemental powers.
Before you're even allowed to swing a sword at a sand monster.
Exactly. You cannot negotiate with these rules.
Yeah.
Let's look at the first part of that ancient contract, the copy and clone traits.
Okay, so if I'm understanding the standard memory model correctly, moving complex data around in a safe environment is usually an incredibly slow, heavy fabrication process.
Very heavy.
It requires allocating new memory space, managing complex pointers so you don't lose track of where the data lives.
Constantly checking dependencies.
Right. It's heavy bureaucratic logistics.
It's entirely bureaucratic, which is something you absolutely cannot afford when you're midair, executing a wall run and about to be swarmed by a horde of enemies.
You do not have time to wait for a blacksmith to carefully forge you a new piece of gear while you are literally falling toward a spike pit.
You'd die. So the ancient forge demands that your powers explicitly implement the copy and clone traits.
And physically, what does that mean?
In the physical reality of the processor, this represents instantaneous duplication of electrical states.
Let's visualize that in the palace for the listener. Imagine you have a specialized magical medallion glowing in your left hand.
Okay.
And you suddenly realize you need its exact power in your right hand to execute a synchronized dual strike against two monsters.
Right. You need two of them immediately.
You don't have time to dismantle the original medallion, carry the pieces across the room, and rebuild it. Because your loadout satisfies that specific trait, you can instantly manifest a perfect bit-for-bit replica of that magic in your other hand.
Exactly. The gear isn't physically bound to one location in a restrictive, software-managed way.
Yeah.
The underlying hardware allows for pure, non-destructive replication at the literal speed of electricity.
Keeping your acrobatic flow completely uninterrupted.
Precisely. But the rule at the forge that is enforced with the most terrifying ruthlessness, the one that really forces traditional programmers to rethink everything, is the output equals self mandate.
Ah, yes. Output equals self. That specific rule feels incredibly rigid. Why is it so strict?
It's a great question.
I mean, in standard programming outside the palace walls, you can take a decimal number, multiply by a whole integer, add a massive floating point variable, and the high-level language just magically figures it out behind the scenes.
It abstracts it all away.
Right. It dynamically creates a new type of container for that number and just hands it back to you. Why does the hardware demand that combining two elemental powers must yield the exact same type of power?
To understand that, we have to look at the physical architecture of the processor itself, specifically the 128-bit hardware registers.
The registers.
Yeah. A high-level software variable is an illusion.
An illusion.
It feels like a flexible box that can dynamically grow or shrink depending on what you decide to put inside it. But a hardware register is not a flexible concept.
It's rigid.
It is a physical, microscopic slot etched directly into the silicon die. It has a finite number of transistors.
Okay.
In the context of our heroic Acrobat, you can think of these registers as rigid, unchangeable, physical slots carved right into your armor, designed to hold specific elemental powers.
So when I am at the forging anvil, or even mid-combat, magically combining two forces.
Right.
Let's say I'm combining a 128-bit vector representing a magical sword strike with another 128-bit vector representing incoming physical damage from a sand monster.
Okay, you're clashing forces.
The ancient forge needs an absolute, ironclad guarantee of what is going to come out the other side of that calculation.
It requires that guarantee because the forge needs to know that the resulting magical output isn't going to suddenly transform into a useless wooden stick.
Or a massive boulder that just crushes you.
Exactly. The result of that mathematical combination must definitively perfectly fit back into that exact same 128-bit physical slot on your armor.
That's to slot right back in.
If you do not explicitly define in your code that the output will be exactly the same physical shape as the input, if you don't declare that output equals self, the forge immediately locks down.
The compiler refuses to build the code.
And the hardware refuses to execute it.
But what is the hardware actually afraid of, though? I mean, physically. If I force it to combine a 64-bit magical strike with a 128-bit block, what physically happens at the microscopic level?
The hardware fears asymmetrical voltage.
Asymmetrical voltage.
You have to remember that the silicon itself is completely blind. It doesn't know what a sword is. It doesn't know what a sand monster is.
Right.
It only sees raw electrical voltage flowing across a wire. If asymmetrical voltage were allowed to be calculated and then forced into a physical slot that wasn't designed for those specific pin layouts,
What happened?
the electrical charge would literally bleed over the boundaries of the circuit traces.
Oh.
In the game world, this means your elemental power would physically explode in your hands the moment you tried to channel it, destroying you instantly.
So the output equals self-contract ensures your magical loadout remains completely predictable.
Predictable, lethal, and geometrically sized for the exact silicon armor slots you're carrying.
That makes perfect sense. The loadout is locked, you've satisfied the ancient rules of the forge, and your armor is fitted perfectly.
You're ready.
Now, you leave the starting area and push deeper into the cursed palace, and immediately you hit the harsh physical reality of the environment itself.
Memory loads.
Yes. You need to get data from the slow, sprawling environment of the main motherboard RAM into the lightning-fast CPU registers where you actually do the fighting.
Which brings us to perhaps the most dangerous step for any bare metal developer. Typing the unsafe keyword
The unsafe keyword.
and executing manual memory load functions. For developers who have spent their entire careers operating in memory-safe languages, typing unsafe is a deeply unsettling moment.
Because you are explicitly telling the compiler to turn off every single safety net.
You are stepping into the most dangerous, trap-filled corridors of the palace. You are turning to your mentor, who has guided you this whole time, and saying, "Stop monitoring me. I am taking total manual control of my physical interactions with the world."
You're on your own.
Completely on your own. When we look at the hardware manuals for SIMD loads, we aren't just politely asking the memory controller to hand us a piece of data.
No.
We are executing what systems programmers literally refer to as a violent gulp.
The violent gulp. That is a fantastic descriptor for the physical action taking place on the memory bus.
It really is.
Contrast that with high-level code. In a safe environment, memory retrieval is a process of polite diplomacy.
You request a variable.
Right. The system pauses, checks the boundaries of the memory allocation, ensures you aren't trying to access something belonging to another program,
It verifies your permissions.
and then it gently hands the data over to your function.
But bare metal SIMD bypasses all of that diplomacy. The violent gulp is you, the hero, executing an elemental dash toward an ancient treasure chest sitting in the middle of a room.
You don't gently open the lid, peer inside, and politely pick up one magical sand crystal at a time to check if it's the right type of magic for your armor.
You don't have the time.
Exactly. You violently rip the lid off the chest and demand a massive, instantaneous 128-bit chunk of power right then and there.
It is a massive burst read that completely saturates the memory bus between the CPU and the RAM.
You're ripping a contiguous chunk of physical memory right out of the environment in a single clock cycle.
And this violent, instantaneous action is exactly why it requires the unsafe override in the code. Because if you do this without meticulously checking the environment yourself first, you trigger something catastrophic.
An alignment disaster.
An alignment disaster, yeah.
Let's break down alignment for the listener, because this is where the physics of the motherboard really assert themselves. The hardware actually expects memory to be perfectly aligned in a physical sense.
Right. It doesn't just expect it. Historically, and often optimally, it absolutely demands it.
Okay.
The physical wires connecting the RAM to the CPU registers the memory bus. They are geometrically designed to pull from addresses that end in specific 16-byte boundaries.
Let's visualize what perfect physical alignment actually looks like in the context of our palace.
Sure.
I would picture perfect alignment as a treasure chest, sitting completely flat, entirely flush on a pristine stone floor.
That's a great image.
When you execute the violent gulp on that perfectly aligned chest, the interaction is flawless. The magical power snaps cleanly out of the chest and perfectly into your armor slots without a single snag.
Exactly.
But what happens if the data is mathematically unaligned? Say the memory address ends in something irregular, like 0 by 04.
When an address ends in an irregular byte boundary, the physical geometry of the data structure is misaligned with the hardware's expected grid.
So in our palace, reality.
This is the ancient treasure chest glitching. It is physically clipping halfway into a solid stone pillar. And remember, because you typed unsafe before you entered this corridor, You stripped away the compiler's ability to warn you about the glitching geometry.
The mentor is gone.
The mentor is gone, so as a hero, you don't know it's glitching.
You just see the chest and you go for it.
Right, you still step up to the chest and try to violently rip it open with full force.
But the physical silicon wires require a clean, mathematically aligned 16-byte grip to pull the voltage cleanly across the bus.
Exactly. When those wires try to grab that misaligned clipping address, the electrical charge literally catches on the stone pillar.
It snags on the physical misalignment of the memory boundary.
It does, and because you bypass the safe software checks, the CPU does not throw a polite error message to your screen.
Doesn't pause time, pop up a dialog box, and suggest you move a few inches to the left to get a better grip.
No. The physics engine of the simulation outright collapses. It crashes catastrophically. The entire game shuts down.
This really highlights the immense pressure of bare metal development. Because he used Unsafe, you accepted total, absolute responsibility for the state of the universe.
Total responsibility.
If you tell the hardware to violently rip open a chest that is clipping into a wall, the electrical routing shears, and the world ends, you have to guarantee the physical geometry of the world before you interact with it.
Which is an incredible mental load for the developer. But grabbing the magical power from the environment is really only half the battle of memory management.
Right, because once you have actually engaged the sand monsters in a room and defeated them, you have to absorb their sand energy.
And store that resulting data back to the RAM to make your progress permanent.
And that introduces our next massive vulnerability.
Yes.
Something that gamers actually feel when a game stutters or drops frames.
The write buffer bottleneck.
Yes. This exposes the almost incomprehensible speed discrepancy between your hyperlethal CPU core, our acrobatic hero, and the slow, lumbering main motherboard RAM.
It all comes down to the fact that storing data takes physical time. For data to be saved, electricity literally has to travel down the copper traces of the motherboard, moving physically away from the processor die to reach the RAM modules.
So in our palace scenario, absorbing the sand energy from defeated monsters back into the permanent environment is an agonizingly slow, heavy extraction process compared to the speed of your lightning-fast sword strikes.
Exactly. The vulnerability lies entirely in the pacing of your acrobatics. You, as the CPU core, operate at multi-gigahertz speeds.
You can unleash dozens of furious, hyper-lethal sword strikes in fractions of a nanosecond.
But the RAM extraction process operates on a completely different timescale. If you unleash dozens of furious acrobatic strikes, defeat 20 monsters in a second, and try to absorb all of their sand energy back to back without intentionally interleaving your movements.
You completely fill up the CPU's internal write buffer.
Yes. The write buffer is essentially a small waiting room for data heading out to RAM. When you fight too fast and try to save too quickly, you're demanding memory extractions faster than the physical motherboard traces can mathematically handle them.
And when that write buffer hits its absolute maximum capacity,
The hardware enforces a hard stall. It physically cuts off the execution pipeline. It refuses to let the processor do anything else until the waiting room clears.
it is a devastating, lethal loss of momentum.
Imagine the scenario in the game.
Right. Your hyper-lethal acrobatic hero is suddenly forced to stand completely motionless in the middle of a trap-filled room.
Doing zero math.
You are taking physical hits from surviving sand monsters. You are completely paralyzed, just standing there waiting for the magical backlog of sand energy to slowly drain into the floor.
All of your teraflops of computing power, all of your theoretical processing speed, it means absolutely nothing if you mismanage your extraction pacing.
To survive at the bare metal level, you have to intentionally pace your acrobatics.
You execute a strike, you do a wall run, you absorb a bit of sand.
You execute another strike while the buffer clears. Managing the physical traffic of electricity is just as important as the combat itself.
It is the combat.
And that concept of maintaining forward momentum leads us directly into the heart of the combat mechanics, the synchronized clones.
We are moving past single, isolated strikes.
Moving past what systems engineers call scalar math.
To define that for the listener, scalar programming is essentially fighting one sand monster at a time. It is one sword swing, one mathematical calculation, processed sequentially.
You strike, you recover, you strike the next target.
It works perfectly fine for small skirmishes or basic high-level applications, but when you are swarmed by a massive horde of physics-driven enemies, sequential striking simply isn't fast enough.
You need a wall of force. You need vertical math.
Vertical math is the entire reason SIMD architecture was invented. Inside the CPU's execution engine, instead of using one calculator, we're utilizing 4 completely separate arithmetic logic units, or ALUs, simultaneously within a single vector register.
Let's visualize this in the palace.
Yeah.
Imagine manifesting 3 magical elemental clones of yourself. You all charge down a crumbling palace hallway, perfectly side by side, shoulder to shoulder. The original hero, Clone 1, occupies lane 0.
Clone 2 occupies lane 1, Clone 3 in lane 2, and Clone 4 in lane 3.
You push forward as a perfectly synchronized wall of force. Clone 1 only strikes the enemy directly in front of lane 0. Clone 2 only focuses on the enemy in lane 1.
You're all completely synchronized in time. Every clone swings their sword at the exact same sub-millisecond interval.
Perfectly aligned to every single clock cycle of the processor.
But here is the architectural detail that absolutely changes everything about how you have to plan your attacks.
How's that?
There is zero crosstalk between these clones.
Zero crosstalk.
It is a state of absolute physical isolation. The microscopic transistors that are physically routing the electricity for lane 0 never, at any point, physically intersect with the transistors processing the math for lane 1.
They are entirely separate, parallel electrical pathways etched into the silicon.
Completely isolated.
Think about the tactical impact of that isolation in a combat scenario. Imagine you and your 3 clones are charging down a crumbling hallway.
Right.
Suddenly, the ceiling gives way, and Clone 1 gets completely crushed by a collapsing solid stone pillar.
Ouch. If we translate that back to computer science, lane 0 just suffered a massive mathematical anomaly.
Like a NaN value.
Exactly. It generated a NaN value, which stands for not a number, or perhaps a severe mathematical overflow error like dividing by 0.
Which completely saturates the register with unusable garbage data.
If you were writing standard, safe software outside the palace, you would write a logical check for this.
Right. The software would pause and ask, is the team okay? Did anyone take damage?
If Clone 1 is hurt, stop the execution and throw an error.
But inside the SIMD pipeline, because of that zero crosstalk physical design, Clones 2, 3, and 4 do not even notice that Clone 1 was crushed.
They have no idea. There is absolutely no shared panic. There is no software logic pausing the simulation to check on the health of the rest of the vector.
The hardware is designed for unyielding throughput.
The surviving clones keep running and swinging their swords with brutal, isolated efficiency. If Clone 1 is dead and outputting garbage data, so be it. The rest of the clones keep clearing the hallway.
It is an incredibly efficient way to process massive amounts of geometry. But that absolute isolation creates a huge problem when you need to use standard logic.
It really does.
If the clones physically cannot check on each other, how do you make dynamic decisions? For example, if you want to know which sand monster in front of you is weaker so you can prioritize your strikes.
Standard programming relies on an if statement for that, a logical branch.
Right. If enemy A is weaker than enemy B, attack A.
But branching in a bare metal SIMD firefight is famously disastrous for performance. Because modern execution pipelines are so incredibly deep, often taking 15 or 20 stages to complete a single instruction, the CPU cannot afford to wait for the math of an if statement to finish before deciding what to do next.
So what does it do?
To keep the throughput high, the hardware relies on a complex mechanism called branch prediction. It literally tries to guess the outcome of the if statement based on past behavior.
It guesses.
It starts executing the guessed path before the original math is even finished, just to keep the forward momentum going.
That sounds incredibly risky. Let's translate a software branch prediction failure into an acrobatic maneuver in the game.
Okay, let's hear it.
A branch prediction is you executing a blind wall run at full speed, completely guessing that there will be a solid stone ledge at the end of the wall.
You're just hoping it's there.
You fully commit to the animation, then the math finishes resolving in the background, and you certainly realize you guessed wrong. There is no ledge. It's just an open abyss.
When that happens, the hardware suffers what is known as a catastrophic pipeline flush.
A pipeline flush.
It realizes it has been executing the wrong instructions for the last dozen clock cycles, and it has to violently throw away all the speculative work it just did.
You have to physically rewind time. You lose all your acrobatic momentum, you rewind all the way back to the start of the wall run, and you are forced to take the other path from a dead stop.
It is an unforgivable loss of clock cycles in a high-performance environment. If you're trying to maintain a locked 60 frames per second, you simply cannot afford to guess wrong.
This is exactly why elite bare metal developers strip out software if statements entirely when writing SIMD kernels.
They replace logical guessing with pure physical force.
Pure physical force.
Specifically, they utilize the max and min hardware instructions. These instructions completely bypass the branch predictor. They don't ask a logical question. Instead, they use literal physical voltage comparators embedded right into the silicon die.
I want the listener to really visualize this difference. Instead of pausing time to logically think about who's going to win a sword clash, the interaction is purely physical.
You and a massive sand monster strike each other simultaneously.
There is no server logic pausing the game to mathematically calculate who did more damage. The hardware routes the electrical data from both strikes directly into a voltage comparator.
Whoever is pushing the higher raw damage number, which correlates directly to a higher electrical voltage in the physical circuit, representing that data, instantly snaps the physical transistor gate open.
And the weaker signal.
It is physically grounded, it is routed into nothingness, and destroyed instantly.
The higher voltage routes directly through the gate, instantly shattering the weaker weapon. The decision isn't made by software logic. It is enforced by sheer electrical pressure.
There are no pipeline flushes, no rewinding time, no guessing at all, just raw, forward kinetic momentum.
It is a brilliantly efficient way to resolve conflict on the die. But raw physical force isn't the only way to survive the palace.
No, sometimes you don't need raw power.
You need unparalleled acrobatic precision. Which brings us to a specialized piece of hardware called the FMA unit and the terrifying issue of floating point drift.
Ugh, the fluid acrobat. This is where the physics of the game world really start to buckle if you aren't careful.
Think about executing the ultimate precision maneuver in the palace, chaining a complex wall run perfectly into a massive, pixel-perfect leap across a bottomless chasm.
Mathematically, for the game engine, this is a complex sequence of operations. It involves multiplying your speed by your angle of trajectory and then adding the gravitational arc of your jump.
If a developer relies on standard scalar hardware units to attempt this two-step process, the simulation falls into what engineers call the double rounding trap.
Let's break down the math there. The first operation, the multiplication of the wall run vectors, generates a highly precise floating point number. This number might have a massive string of trailing decimals representing the exact microscopic angle of the hero's foot.
But remember the unbreakable rules of the ancient forge we talked about earlier. The 32-bit register is a rigid physical space. It's a bucket with a fixed size.
You physically cannot fit 50 trailing decimals into a rigid 32-bit slot on your armor.
You absolutely cannot. So the hardware is forced to physically chop off those trailing decimals.
It truncates the number, sacrificing microscopic accuracy, just to fit the intermediate result of the wall run back into the holster before it can even begin to calculate the leap.
You lose a microscopic degree of physical accuracy before your boots even leave the wall.
Then it takes that slightly degraded physics data, routes it back out into the adder circuit for the leap calculation, finishes the math, and has to chop off decimals and round the final result again to store it.
You are rounding the physics of the character twice in a single frame of the simulation.
Now, a single microscopic error doesn't matter for a small hop. The human eye wouldn't notice it. But over a massive frame-by-frame acrobatic sequence where the output of one frame becomes the input for the next frame,
those microscopic rounding errors gallantly compound.
The simulation literally loses its grip on mathematical reality. This is floating point drift.
We've all seen this happen in older games. Your perfectly timed, flawless leap suddenly destabilizes. Because the map degraded over 60 frames, the hero's physical hitbox is no longer where the visual model is.
And you inexplicably phase completely through a solid stone pillar, plunging into the abyss. The engine betrayed you.
So how do modern hardware engineers stop that drift and anchor the physics flawlessly?
They created a highly specialized hardware pipeline to bypass standard math entirely. The FMA bypass, which stands for Fused Multiply Add.
Fused Multiply Add.
The FMA unit is a massive, uninterrupted internal electrical chain physically etched onto the silicon die. When you execute an FMA instruction, the electricity flows straight from the multiplier circuit directly into the adder circuit.
It never stops to park the data in a rigid 32-bit register in between the two operations.
It is one continuous, fluid, acrobatic motion.
You never stop to plant your feet and store the data in your armor.
Exactly. Because the electricity never parks in a fixed 32-bit register, the hardware does not have to truncate or round the intermediate step.
It keeps the precision.
The FMA unit contains wide internal accumulators that hold the calculation at an expanded, infinite internal precision. It calculates the entire sequence of the wall run and the leap in one fluid, uninterrupted electrical flow.
So it only rounds exactly once.
Right at the very end of the entire physical chain.
Exactly as your boots hit the far ledge. That single fused hardware instruction anchors the literal physics of the game world flawlessly. It eliminates the double rounding trap entirely.
It is a true masterpiece of precision engineering.
And that concept of bypassing standard sequential math to achieve a performance advantage leads us beautifully into our next section, ancient magic hacks.
We're talking about manipulating data architectures without performing actual arithmetic, purely to save precious clock cycles.
One of the best examples of this is the absolute value function, or ABS. If you are writing standard high-level code, getting the absolute value of a number requires logical branching.
You check if a number is less than 0. If it is, you multiply it by -1 to make it positive. If it's already positive, you do nothing.
But wait, we just established that logical branching causes pipeline flushes, and routing data through a multiplier circuit just to flip a sign is incredibly slow. How do bare metal developers bypass this?
They bypass it entirely by exploiting the architecture of the IEEE 754 floating point standard.
IEEE 754.
To clarify for the listener, that is the universal technical standard that dictates exactly how computers represent fractional numbers in binary. Under this strict architectural standard, a 32-bit float isn't just a random jumble of ones and zeros.
It is heavily segmented into specific roles.
And the 31st bit, the very last microscopic bit at the far end of the physical chain, is uniquely designated as the sign bit.
So that single bit controls the entire polarity of the number.
Exactly. If that specific microscopic transistor holds a 0, the hardware interprets the entire massive number as positive. If it holds a 1, the entire number instantly becomes negative.
Wow.
Hardware engineers realized they didn't need to do complex arithmetic to heal a negative status. They just needed to execute a targeted surgical strike on that single physical bit.
Let's map a negative sign bit to a deadly palace trap to see how this plays out in real time. Imagine you get hit by a cursed dart fired from a wall trap.
Okay.
This dart inflicts a negative sign bit on your health pool. Let's call it a cursed sandrot. Your vision blurs, and you are rapidly losing health over time.
If you use standard software healing math, multiplying your health by -1 to reverse it, it is slow and burns valuable clock cycles while you are still taking damage.
But an elite Acrobat inside the processor uses a rogue elemental hack, the Bitwise AND mask.
Specifically, they use a hexadecimal value of 0/7 FFFFFF. If you write that mask out in raw binary, it looks like a single 0 followed by exactly 31 consecutive ones.
Okay, so 1031 ones.
When you execute a hardware bitwise AND instruction, the processor physically overlays your acrobatic health data against this binary mask.
And to understand the physics of this, the fundamental rule of an AND logic gate is that both incoming electrical signals must be a 1 for the output voltage to pass through.
If either signal is a 0, the gate closes and outputs 0.
So as the hero, you unleash this magical elemental cleansing blast, which is the Bitwise mask, because the bottom 31 bits of the mask are all ones. Your base health, your armor stats, your acrobatic momentum, all your actual numerical combat data hits those ones.
The physical AND gates see the data, see the ones in the mask, and let the voltage pass through completely untouched.
But that cursed very first bit, the sign bit carrying the deadly sandrot, it hits the single 0 located at the very top of the mask.
And because of the physics of the AND gate, the voltage is flatly denied. It doesn't matter if the sandrot was a 1 or a 0, anything combined with a 0 in an AND gate is instantly vaporized into a 0.
The single 0 in the mask vaporizes the sandrot instantly at the literal speed of electricity. The negative sign is stripped away, and you step through the logic gate completely cleansed.
0 arithmetic was performed. There was no multiplication, no checking if you were sick or healthy, just pure structural manipulation of the silicon gates. It is a beautiful, ruthless optimization.
It is incredibly elegant. However, deploying these specialized architectural hacks requires absolute, strict discipline from the developer, specifically regarding something called ALU uniformity.
Yes. Modern processors are incredibly complex cities, and they have entirely separate physical pipelines for floating point math, which handles decimals and complex physics, and integer math, which handles whole numbers and basic counting.
Mixing them triggers a devastating performance penalty. Let's map this penalty to the combat flow. You are in a flawless acrobatic rhythm, dodging traps, slicing through monsters with your lightweight curved sword.
This sword represents the floating point pipeline.
Right. The physics of your movement are flowing beautifully, but suddenly your code is poorly optimized, and it demands a heavy integer calculation to figure out an array offset or count the number of enemies left.
You just demanded a massive weapon swap mid-air.
You are forcing the hero to put away the fast, lightweight sword and seamlessly unholster a massive, cumbersome, incredibly heavy warhammer while still in the middle of a backflip.
The hardware physically halts. It cannot process integer math in the floating point unit. It has to pull the electrons out of the floating point registers, physically push them across the massive silicon die to the entered unit, wait for the integer ALU to spin up and perform the calculation.
And then route the data all the way back across the die.
It is an agonizing, incredibly slow animation delay that completely stalls your entire acrobatic flow. You are left hanging midair, waiting for the massive hammer to swing, completely vulnerable to attack.
The lesson here is that you have to pick your weapon float or integer and stay exclusively in that pipeline to survive.
Consistency is survival, but even if you maintain perfect discipline, even if you stay entirely within the optimized floating point pipeline, there is one mathematical enemy that absolutely terrifies hardware engineers.
It is the ultimate bullet sponge of the processor. Division.
Hardware division is an absolute nightmare for performance. We just talked about how a beautifully optimized FMA acrobatic leap might take only 4 clock cycles to execute perfectly.
Right.
Asking the CPU to physically divide one floating point number by another forces the hardware into an inherently iterative looping nightmare.
To understand why it's so slow, you have to realize that division, by its very mathematical nature, cannot be perfectly parallelized into a single massive wave of logic gates.
Multiplication can be blasted through a massive grid of adders instantly, but division forces the hardware to loop. It has to guess a quotient, multiply it back to see how close it got, subtract that from the original number, check the remainder, physically shift the bits over, and do it all over again.
Over and over.
This iterative process costs anywhere from 25 to 80 agonizing clock cycles, depending on the architecture.
Let's visualize just how terrible an 80-cycle delay is in the heat of the game. You are mid-combat, actively dodging swinging scimitars from sand monsters, and you realize you need to calculate the exact physical distance to launch a freezing spell at a distant water spout to create an ice pole to swing on.
A classic maneuver.
Using hardware division to calculate that specific distance is like dropping your sword, pulling out a physical metal measuring tape, walking it slowly all the way across the crumbling room to the water spout, reading the measurement, and walking all the way back, all while monsters are actively attacking you.
It is 80 cycles of absolute dead air.
The simulation would stutter to a completely unplayable halt. You would die before you finish measuring.
So, to bypass the 80-cycle measuring tape, engineers utilize a highly specialized, almost magical instruction called RSQRT, which stands for reciprocal square root.
RSQRT.
When the hardware encounters this specific instruction, it doesn't even attempt to do the iterative math. Instead, it accesses a hard-coded cheat sheet etched directly into the silicon at the factory. This is known as a hardware lookup table.
It is literally like channeling the ancient, omniscient knowledge of a djinn. You don't pull out the tape measure, you ask the djinn.
The djinn's magic instantly accesses this ancient table burned into the physical world, and it gives you a 99% accurate, instinctual guess of the exact distance to the water spout in just 2 clock cycles.
2 cycles instead of 80. It's an unbelievable performance game.
It is a massive game, but there is a catch. A 99% accurate guess is incredible for a human, but it isn't perfect for a physics engine.
If your freezing spell misses the exact center of the water spout by even 1%, the spell hits the stone wall behind it, the water doesn't freeze into a pole, and your acrobatic leap ends with you falling into the abyss.
We need absolute mathematical perfection.
Yeah.
We must close that 1% error gap, but we absolutely cannot use division to do it.
Which is exactly where one of the most brilliant mathematical workarounds in computer science comes in. The Newton-Raphson method.
Yes. The Newton-Raphson method is a calculus-based root-finding algorithm. Instead of dividing, it uses rapid calculus tangent lines executed via our blazing fast FMA multiplication and subtraction units to refine the guess.
It essentially draws a mathematical line that rapidly closes the gap of the error without ever triggering the slow division circuitry.
I love how this translates into the game world. In the game, Newton-Raphson acts as an ultra-fast magical aim assist. The Djinn gives you the rough bounding box of the target in 2 cycles. You are aiming generally at the water spout.
Then the first iteration of the Newton-Raphson algorithm kicks in. Using pure FMA speed, it violently snaps your aim from the edge of the bounding box directly toward the center of the waterspout. That takes maybe 4 cycles.
You run it one more time, and it snaps perfectly to the dead center. In total, over about 8 lightning-fast clock cycles, you achieve pixel-perfect precision.
You completely bypass the 80-cycle tape measure. The game engine remains completely seamless, maintaining a locked, buttery smooth 60 frames per second, entirely because we replaced iterative hardware division with a physical silicon cheat sheet and a calculus-driven refinement.
It's incredible how much effort goes into avoiding a single math operation. But calculating distance and trajectory is only one part of the fight. We also have to handle complex defensive logic.
And that brings us to the concepts of stone armor and magical routing. Earlier, we established that we absolutely cannot use if statements because rewinding time for a branch prediction failure destroys our momentum.
So if we can't use if statements, how do we handle complex logic across our 4 elemental clones simultaneously?
This is the crux of SIMD programming. What happens if clone 1 is facing a massive attack and needs to block, which is a true condition, but clone 2 has an opening and needs to keep attacking, which is a false condition?
The 128-bit vector as a whole is in a state of quantum Boolean confusion. It cannot be singularly true or false. To resolve this without triggering a branching penalty, the hardware uses comparison instructions like comp.
But crucially, clomp does not return a software Boolean word like true or false. It returns a physical bitwise mask.
Let's dive into the physics of this mask. We've called it the wall of electricity. Tell us how this mask physically manifests on the die.
If the mathematical condition is true, meaning clone 1's health is lower than the incoming damage, and it needs to block the hardware floods that specific 32-bit lane with absolute maximum voltage, every single microscopic transistor in that lane flips to a 1.
It literally becomes a solid physical wall of electricity.
But if the condition is false, clone 2 is safe and keeps attacking the voltage in lane 1 drops to absolute 0, a complete void of zeros.
Let's translate this raw voltage into your magical stone armor in the game. If the condition is true, your stone armor activates, manifesting visually as a solid, physical wall of glowing 1's pure electrical defense.
If the condition is false, the armor remains shattered, leaving an empty dark void of zeros around that specific clone. But how does the hardware actually route an incoming attack using this armor?
We take that massive 128-bit mask of alternating 1s and 0s, and we feed it into a specialized hardware instruction called blend. The blend instruction lays this electrical mask down over the circuitry like a literal physical stencil.
So a sand monster swings a massive heavy scimitar at you. There's absolutely no software logic deciding if you take damage. The compiler is not involved. There is no if statement checking your block status.
The scimitar's damage data physically hits that electrical stencil at the speed of light. If the solid wall of 1s is there, if the stone armor is active, the blade's data bounces harmlessly off the electrical wall and is routed into a blocked pathway. It registers 0 damage to your health pool.
Exactly. The physical presence of the voltage deflects the data. But if the armor is shattered, if that specific lane is a void of zeros, the blade's data finds no physical resistance. It passes cleanly through the empty transistor gates and is routed directly into your health bar register.
It is raw, deterministic physical routing. The electricity simply bounces off the stencil or passes through the void without a single branch prediction ever occurring.
It's mesmerizing when you think about it. Just pure, deterministic routing of electrons. Which leads us to the complexities of navigating the battlefield when things aren't just moving straight forward. We need to talk about sideways momentum and spatial routing.
We established very early on that vertical math pushes straight down the pipeline perfectly. Clone 1 handles lane 0, clone 2 handles lane 1, and they never talk. But what about lateral communication, what engineers call horizontal math?
What if clone 1 absolutely needs to share a piece of magical data with clone 2?
This invokes one of the most painful bottlenecks in CPU architecture, the shuffle engine. The CPU pipelines are rigidly wired to push data forward stage by stage toward completion. To share data laterally across the lanes, it's not a simple request.
Not at all. To execute a horizontal move, the CPU must physically halt the forward execution pipeline. It extracts the voltage from lane 0, routes it backward through a complex physical crossbar switch on the silicon die, physically rotates the bit alignments to match the new destination, and then drops the voltage into lane 1.
I want you to visualize the total destruction of your momentum in the game. You are in a dead sprint forward, executing flawless synchronized acrobatics with your clones, but suddenly you have to screech to a complete halt, turn 90 degrees sideways, and physically throw a magical health potion to your clone.
It absolutely shatters your forward flow. Elite developers avoid horizontal math at all costs.
You avoid it whenever possible. But sometimes data distribution across the vector is mandatory. What if you defeat a boss, if you're a massive magical power-up, and you need to give that buff to all your clones instantly? You cannot have one clone run sideways to hand it out sequentially. That would take too many cycles.
For a uniform distribution, you bypass the slow crossbar switch entirely and use an instruction like vBroadcasts, which developers affectionately call a splat.
The splat. Mechanically, how does this work without ruining momentum?
It triggers a massive, localized electrical short circuit. It takes that single magical power-up value from one register and violently blasts it across all 4 lanes simultaneously via dedicated broadcast wires.
It's an instantaneous EMP of beneficial data. A massive radial burst. In a single clock cycle, without any lateral running or halting of forward movement, the magical buff is perfectly mirrored across all clones. It's instant, uniform amplification without breaking stride.
It is incredibly fast. But what if you don't want a uniform burst? What if you need surgical target reassignment? Say you need Clone 1's weapon in Clone 3's hand and Clone 4's shield in Clone 2's hand. That requires the ancient switchboard, the SHUPS instruction, and its vital 8-bit control byte.
What makes the control byte so special?
The control byte is an immediate value, meaning it is hard-coded directly into the machine code at compile time. It is not dynamically generated during the fight. Before the maneuver even executes, those specific 8 bits tell the hardware exactly where every single lane should pull its data from.
Because it is hard-coded, the physical crossbar switch can pre-align its physical pathways before the data even arrives. It locks the physical routing into place, executing the complex reroute instantly without logic delays.
It requires immense foresight from the developer to hard-code that routing. But the most punishing maneuver of all, the one that truly demands sacrifice on the battlefield, is the inserts instruction.
Yes, the insertion penalty. Inserting a single, newly calculated scalar value into just one active 128-bit vector lane without accidentally corrupting the incredibly high-voltage data flowing through the other 3 adjacent lanes requires an incredible amount of physical control over the silicon.
To force a single new target or a new weapon into just one lane, the other 3 clones must completely lock down. They must sacrifice all of their forward momentum to project highly protective magical masks over their specific areas of the register, ensuring their physical voltages don't accidentally fluctuate and corrupt the new data coming in. The CPU forcefully clears the target lane and then silently crams the new data in.
It is a massive, highly coordinated pipeline stall just to update one single clone.
The physical stress of routing data laterally is intense. It's a logistical nightmare for the processor. But honestly, all of the pipeline flushes, all the shuffle penalties, it all pales in comparison to the ultimate enemy out there in the Palace environment, the final boss of bare metal optimization.
The 500-kilometer Armory. We are talking about physical distance and latency. We have to connect everything we've talked about today to the grand macro scale of the hardware layout.
The physical distance between the CPU execution core, where your clones are actively fighting and swinging their swords, and the main motherboard RAM is the great equalizer of all computer performance. Let's quantify this latency.
The L1 cache is a tiny pool of memory bolted directly to the execution core on the die. Because it is so close, it is virtually instant. It takes maybe 1 to 3 clock cycles to access data there.
In our Palace world, the L1 cache is the sword currently gripped tightly in your hand. It is immediately available. But the L1 cache is microscopic. It can only hold a few weapons. When you enter a new room and need new environmental data, you suffer a cache miss. The L1 cache is empty. You have to fetch the data from the main RAM.
And the main RAM is a sprawling weapons armory located 500 kilometers outside the palace walls.
To a human physically on the motherboard, the RAM sticks are maybe an inch or 2 away from the CPU socket. But to a processor executing billions of clock cycles a second, that inch is planetary in scale. If the CPU needs data from RAM, it must halt the mathematical execution entirely. The electrical signal travels down the motherboard traces, accesses the RAM cells, waits for the memory controller to find the data, and drags it all the way back across the bus.
That round trip takes roughly 300 clock cycles.
300 cycles of absolute dead air. It is the equivalent of freezing mid-jump. in an intense boss fight, casually walking 500 kilometers out to the armory, picking up one specific sword, and walking 500 kilometers back. In those 300 cycles, you could have executed thousands of complex acrobatics, blocks, and strikes.
It is a complete and total murder of your performance.
Oh.
When you play a game and it stutters horribly right as you open a door to a new area, this 300-cycle armory walk is exactly what you are experiencing. You are feeling the physical speed limits of the motherboard.
Which is exactly why elite bare metal engineers will do absolutely anything, use any trick available to avoid querying RAM. They treat it as an absolute last resort. This desperation leads to an amazing hardware trick. Let's say you just pulled aggro from a massive sand monster boss and you need to reset your threat level to absolute 0. But wait, fetching a vector of zeros from the RAM armory takes 300 cycles.
You can't jog 500 kilometers just to pick up a cloaking spell. The boss will crush you. How do you instantly reset your threat to 0 without talking to RAM?
You use the XORPS instruction, the exclusive OR logic gate. The hardware runs an active register against itself, using a bitwise XOR logic gate. Now, let's look at the physics of an XOR gate. The fundamental rule of an XOR gate is that it only outputs voltage, a 1, if the two inputs are different. If the inputs are identical, if they are both 1s or both 0s, the gate outputs a 0.
And since we are running a register perfectly against itself, every single bit perfectly matches. Therefore, the entire 128-bit vector instantly flushes to absolute 0 without ever sending a single signal out to RAM.
It is a tactical masterpiece. You have pulled the attention of a massive sand monster boss. Instead of running 500 kilometers to find a 0, you magically summon a perfect, identical clone of yourself right on top of your own body. Because of the physical laws of the XOR gate, identical forces instantly vaporize each other.
You flash into absolute nothingness in a single clock cycle, dropping the monster's attention to 0 instantly.
It is a brilliant bypass of the RAM penalty. But you can't XOR complex environmental geometry into existence. A 0 is easy. But eventually you must load heavy, unpredictable room data, new monster models, new trap layouts from the RAM armory. How do you survive the 300-cycle wait when you have to open a heavy door to a new area?
You have to send magic into the future. You use the PREFETCH red instruction. Imagine you are furiously fighting a horde of enemies in a long hallway. If a novice developer just finishes the fight, runs up, and kicks open the closed door to the next room, they suffer a massive cache miss. They stand completely frozen in the doorway for 300 cycles while the RAM slowly fetches the monster data for the new room.
It is absolute suicide. The monsters in the new room will hit them before the physics engine even registers they can move.
An elite bare metal engineer survives by anticipating the threat. While the hero is still actively executing the combat loop in the hallway, fighting the current enemies, the code sends an electrical pulse out to the memory controller before the data is actually needed. You are warning the RAM. You are warming up the cache lines in the background while the CPU is still busy doing math.
It is the ultimate display of acrobatic foresight. While you are still swinging your sword, finishing off the last enemy in the hallway, you send a tiny wisp of sand magic under the closed door ahead of you. It aggroes the monsters in the next room, dragging them toward the door. The memory controller is doing all the heavy, slow logistical lifting on the motherboard parallel to your fight.
By the time you finish your fight, execute a flawless backflip, stack up against the wall, and kick the door open, the execution loop has perfectly caught up with the memory fetch.
The data isn't 500 kilometers away anymore. The monsters have been dragged right to the threshold. The room geometry is sitting hot and ready in the microscopic L1 cache right on the die.
0 latency. You strike instantly as the door opens. You completely masked the 300-cycle penalty. The transition between rooms is flawlessly smooth. No frame drops, no stuttering. It is breathtaking choreography of electricity across space and time.
And that perfectly synthesizes our journey today. We stripped away the polite, safe software maps. We realized that underneath the compiler warnings, underneath the high-level languages, surviving this simulation relies entirely on mastering the raw physical constraints of the silicon.
Every fluid jump, every perfectly frozen water spout, every single deflected scimitar strike you experience in a high-end simulation is supported by an invisible, microscopic war zone of electrical forces. It is about physically routing raw voltage into stone armor, blasting elemental masks to cure status effects without branching, dodging the grueling 500-kilometer walk to the armory, and sending magic into the future to completely mask hardware latency.
It reminds us that there is a profound physical beauty to this architecture. The physics of the silicon, the voltage thresholds, the transistor gates, the crossbar switches are resolving billions of times a second in perfect concert to maintain the fragile illusion of your virtual world.
Which brings us to a final provocative thought for you to ponder. We are rapidly entering an era where high-level generative AI agents are taking over writing standard, safe code. They can map out the safe routes outside the palace in seconds. They can write Python or JavaScript faster than any human.
But the sheer unforgiving mechanical reality of the silicon. The pipeline flushes, the alignment crashes, the 300-cycle RAND latency remains entirely untouched by AI language models. The physical laws of the stone and the sand do not care about predictive text algorithms. They require a master who understands the electrical physics of the die.
As we demand increasingly photorealistic, mind-bending real-time physics in our virtual worlds, will this ruthless, handcrafted bare metal artistry become a forgotten dark magic? Or will the rare engineers who can physically choreograph electricity like an acrobatic master, manipulating time and elements, become the most irreplaceable minds of the future?
It is something to think about the next time you execute a flawless wall run or notice a game perfectly maintaining 60 frames per second during a massive battle. Keep looking beneath the surface.